Alright, we'd like to convert this second order differential equation into a first order system, and then we want to find the critical points of that system. We'll then use Maple to draw a phase portrait and slope field for this first order system that we converted into, and then we'll visually identify the type of each critical point. So when we convert the second order differential equation into a first order system, well, we need two variables because of the second order, so let's let one of our variables just be x, and then we'll take x prime, we'll make that y, and then notice our x double prime will equal y prime. And so we can go ahead and take our equation and solve for x double prime. So x double prime is equal to, well, negative 2x prime minus x minus 4x cubed. And so with this in hand, we can write down our system. So x prime equals y, and what does y prime equal? Well, y prime is the same thing as x double prime, so y prime is going to equal negative 2 x prime, but what's x prime? X prime is y, so we can replace that with y, minus x minus 4x cubed. So there's our equivalent first order system. We now want to find the critical points of this first order system, and so we go ahead and do that by taking x prime equal to 0 and y prime equal to 0. And so the first equation becomes nothing but 0 equals y, I guess that's convenient, and our second equation becomes 0 equal to negative 2y minus x minus 4x cubed. And we want both of these to be true at the same time, so that forces y to be 0, and so then our second equation becomes 0 equal to negative x minus 4x cubed, and it looks like we can factor out a negative x here, so we have negative x times 1 minus plus 4x squared, and so let's go ahead and solve this. We get x equal to 0, and 1 plus 4x squared equal to 0, which implies that x would equal what? Plus or minus 1 over 2i. And since we care about only real valued solutions here, x and y represent solutions of our system, we can go ahead and throw out this imaginary one. There's no place for it in our phase portrait of x and y. So it looks like we only have one critical point that we really have to care about. So the critical point here is the origin 0, 0. Now let's go ahead and load up Maple here and plot a phase portrait and look at some trajectories and try to get a feel for what the behavior of the trajectories in this nonlinear system are near this critical point 0, 0. So I've gone ahead and entered in our system into Maple here. X prime was equal to y, and y prime was equal to negative 2y minus x minus 4x cubed. And so we certainly have a nonlinear system here. And let's go ahead and graph the slope field. And so there's the slope field. We see all the arrows in the slope field seem to be pointing relatively towards the origin. So that makes me suspect this is going to be a stable equilibrium. But let's go ahead and click in some trajectories and just see what they're doing. Alright, so they look like they're kind of spiraling around, and in particular if we look at this one as it moves forward, it kind of comes up and around, and that's kind of what all of them are doing. And so looking at this thing, it appears that the behavior visually around the equilibrium 0, 0 is behaving very much like a stable spiral.